Hi everyone, welcome to GemChem. Now previously we had dealt with estimation of iron 2 plus salt using Mohr salt solution, and there we used KMnO4 solution. Now today in this video, that is Redox Chemistry part 3 video, here we will deal with estimation of Fe2 plus salt using K2Cr2O7 solution. Now we will also deal with criteria for a redox indicator and BDS indicator will be discussed. Now before starting, if you have not watched the previous parts of redox chemistry, you can watch it. I will give the link in the description box as well as the I button present above this video. Now if you are new to this channel, do not forget to subscribe and always press the bell icon for regular updates on uploaded videos. Now let us start today's video. Now for estimation of iron 2 plus salts, we need K2Cr2O7 solution. Now first of all, K2Cr2O7 solution is known as potassium dichromate, right? This is a primary standard. Unlike KMnO4, which were secondary standard, it is a primary standard, right? So it has a color but not used as an indicator. So why is it so? Right, we have to know this. Now this is a good viva question. Also for practical cases, we'll deal with these questions in our practical classes also, right? So these videos of redox chemistry is mainly based on the theory portion as well as the questions asked for viva. So let us see another question, that is, explain whether K2Cr2O7 solution will be able to oxidize a solution of Fe2 plus salt, and also explain whether this reaction is favored in acidic pH or alkaline pH. We have dealt with such a question in our previous video, right? So today we will deal with K2Cr2O7 solution. Now first we need to write the equations for the redox reaction. So first is for Cr2O7 2 minus plus 14H plus 6 electron produces 2 Cr3 plus 7 water, and the standard electrode potential is 1.33 volt. Now for this one, it is Fe3 plus electron produces Fe2 plus, and the standard electrode potential is 0.77 volt. So what is the net required or expected equation? It is 1. If we take this one 1 and this one as 2, then it is 1 minus 2 into 6 is the expected reaction, and it will come to be as Cr2O7 2 minus plus 14H plus 6 Fe3 plus produces 2 Cr3 plus 7 H2O plus 6 Fe2 plus. Right, now we need to get the amount of potential, right? So delta E can be written as E1 0 minus E2 0. Now previous day we have already learned that stoichiometry does not matter for this case. So it is 1.33 minus 0.77 volt, and the answer comes to be as 0.56 volt. Now we will write the equation, right? So what is the equation? Let us see. We will write delta E equals to delta E0 minus 0.059 by 6 log Cr3 plus Fe3 plus 6 in the power Cr2O7 2 minus H plus to the power 14 and Fe2 plus to the power 6, right? And the delta EF, that is formal potential, is equals to delta E0 minus 0.059 by 6 log 1 by H plus concentration to the power 14, right? Now the delta EF is equals to delta E0 minus 0.059 by 6 into 14 pH, right? This is what is required form of the equation. So now if we take the pH at, suppose, pH equals to 1, then delta EF comes to be as near about 0.42 volt, and it is favored because positive potential value. So delta GF is negative. Similarly, if we consider for at pH equals to 10, then delta EF comes to be as near about minus 0.84 volt, and here delta GF is positive. Thus, we see that this reaction is favored in acidic pH and not in alkaline pH, right? Now we will see about this one. That is, if we consider this one now for titration, then here in the conical flask we take Fe2 plus solution and 0.5 molar phosphoric acid and 2 normal H2SO4. Acid is required to maintain the acidic pH, right? Next we will take a indicator which is a redox indicator, BDS indicator, and here we will take K2Cr2O7 solution in the burette. Now the value of E0 of BDS indicator is 0.84 volt, right? And we know that the value of Cr2O7 solution is near about, for chromium it is near about 1.3, and for E0 of iron system it is about 0.77 volt. So this indicator lies somewhat between these two ranges, right? Now why phosphoric acid is used? It forms complex like this with Fe3 plus ions, thus substantially lowers the potential, and the formal potential of this system in this condition, that is 0.5 molar H3PO4 solution plus 2 normal H2SO4, becomes 0.61 volt. So actually what it is doing, it is increasing the gap between the indicator and the system as well as the chromium, right? Because if we look carefully here, it is 0.84 and 0.77, the gap is little lower, but when it is 0.84 and 0.61, the gap becomes higher, right? Now what is a redox indicator? Redox indicator is redox active substance which indicates the end point of a redox titration by changing its own color. Now if suppose this is an oxidized form, on taking up electron, maybe some amount of electron like N is an integer, then it forms a reduced form, In red. Now what is the criteria for redox indicator? It should be redox system itself, where color of oxidized and reduced form of indicator should be distinctly different from each other, right? And the standard reduction potential should lie in between titer and titrant value. That is what you are taking in the conical flask as well as what you are taking in the burette, right? And for sharp detection of this equivalence point or the end point, formal potential of titer and the titrant system should differ at least of 0.15 volt as compared to the indicator system. Okay, now color of one form of indicator will be visible to human eye if concentration of that form is at least 10 times greater than the concentration of other form. And the equivalence point, that is the last point, the equivalence point of the given titration should preferably lie within color change interval of the indicator. Okay. Now we will see what is BDS indicator. The full form of BDS indicator is barium diphenylamine sulfonate. Okay. So this is the structure. We have two phenyl rings attached to a nitrogen, and here there is a sulfonate group. Now see this one. This is the reduced form. Now when it is reduced form, it is colorless, and when it gets oxidized at about this potential, it becomes blue violet. Now barium 2 plus has nothing to do with the redox titration, and SO3 minus is hydrophilic substituent. Why it is used? It is used to hold the indicator in water and restricts one para position from the bond formation. Okay. Now see this one. This is the substance, that is BDS, right? So it loses 2 electron and 2 H plus to produce this kind of structure. Now this is colorless. When it again loses 2 electron and 2 H plus, then it becomes this unit. And we should look into this carefully, that is this region has a double bond in conjugation. Since it is conjugation, so what we can expect? We can expect a chromophore, that is there is a color present in it. So this is the reason why this part is colored. Okay. Now we will see what is the indicator range. How we can determine the indicator range. Now first, for this case, if we consider this titration which we are dealing with, that is Fe2 plus versus K2Cr2O7 solution, what is the equivalent point? It is actually 6 into 1.3, that is 6 electron transfer of iron case, but the potential is taken for the chromium system, and then plus 1 into 0.77 volt by 6 plus 1, and this is equals to 1.25 volt. And if we consider about the indicator, then EIN of the indicator has a range of at about plus minus 0.059 by N. Okay, so the range is near about 0.82 to 0.88. Okay, now we can note that here the range is not in between this one, right? So equivalence point lies far away from this one. So we add normally glacial acetic acid or NH4HF2 so that this indicator can be used, and thereby it reduces the formal potential of the system to such an extent that under this condition the equivalence point falls practically within the color change interval of indicator. So another component which we add during this titration is glacial acetic acid or NH4HF2. Now see this one, solution color is pale green previously, and when the titration is being performed we get a violet color. So after all the Fe2 plus is oxidized to Fe3 plus, dichromate oxidizes the indicator and the end point is marked by a sudden change of color from pale green to violet. We can see the color change. This is a pale green and this is violet. K2Cr2O7 has color but not used as self indicator. Why? So you can think of it and tell me in the comment section what is the answer, and I will answer this question in the next video. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.